Okay, welcome to lecture here. We're going to continue on chapter 14. So continuing on here, talking about acids and bases. As soon as everybody gets in, we'll start here. Okay, so we were talking about acids and bases in this chapter here. We started at the end last time. So a reminder that basically an acid is a substance that can produce H plus ions or H3O plus ions, and H plus ions are and H3O plus are essentially the equal to each other in terms of acid and base chemistry. So they're used interchangeably. They're also used in formulas interchangeably, also equations as well. But they basically represent an acid. So anything that's able to sort of produce those guys on the product side of an equation, usually you have sort of an acidic type solution happening. While a base is something that can produce hydroxide OH minus ions in solution. And these are free H pluses, free OH minuses is again what basically will determine whether or not the solution will be acidic or basic. And as we talked about, I think last time as well, that's sort of what you want to look for on the product side of an equation, and being able to write these reactions are really important for that. Again, if you see H plus or H3O plus on the product side, probably more acidic, and especially in terms of calculations, an acidic type calculation. While obviously, if you see hydroxide there on the product side, you're probably dealing more with a basic type calculation when you're doing it. And again, that's why, as we talked about, it's really important to make sure that you do understand how to properly write these equations and reactions so that you can kind of do the math part right, kind of makes sure that your answer makes sense as well. So it's really important to, get those formulas and equations down so that you can kind of do the math part of it right. We talked about pH and the pH scale, which runs from 0 to 7 to 14. Less than 7 is acidic. More than 7 there is basic. At 7 is neutral. And we saw that relationship for Kw, which is a concentration of H plus times concentration of OH minus equals 1 times 10 to the minus 14. That allows you to calculate either the H plus, the acid part of the solution, or OH minus concentration, which would be like the basic part of the solution. And the relationship of those two things are, as one goes up, the other goes down. So as the H plus concentration goes up, OH minus goes down, and vice versa. So as one goes up, the other does go down. And that relates into our pH. As the H plus concentration increases, the pH gets smaller, and vice versa. As the H plus concentration goes up, the pH will also. As the H plus concentration goes down, the pH will go up, and that means as the H plus goes down, the OH minus concentration is getting larger. So we could calculate the pH by taking minus the log of the H plus concentration. We also saw that we could calculate what's known as the pOH by taking minus the log of the OH minus concentration. And the nice thing about those two is if you add them together, the pH plus the pOH, it does equal 14. So it gives you a little bit of options as to how to solve certain problems. You may not even have to use Kw like we talked about last time. You could kind of use pH and pOH to help you get there. And that is because the last sort of thing I think that we talked about was that if you do have the pH given to you, you can get the H plus concentration from that by taking inverse log of the minus pH. And that is 10 and a caret usually when you hit it on your calculator, and you want to make sure it's negative. And you could also get the OH minus concentration from the pOH by pretty much the exact same calculation. You would take the inverse log of the minus pOH, and that will give you the OH minus concentration. So again, it gives you a little bit of variety in terms of how you could solve those problems. You could do it either way. You could use Kw, not use Kw, use the inverse log part of it. Again, all should really give you the same answer regardless of which one you choose. Again, as long as you don't do like a lot of crazy rounding or anything like that. Remember, though, that when you are asked if it's acidic, basic, or neutral, there is only one answer for that question. And you do want to look at the pH scale because that's usually what people have in their head. Again, the pOH scale runs opposite. So you have a low pH, you have a high pOH, and vice versa. A high pH, you have a low pOH in that particular case. Any questions on any of that stuff that we talked about, I think, last time? Okay. And last reminder on that stuff, again, as well, you want to make sure that you are using your exponent button when you're punching these things into your calculator. Again, if you're finding yourself getting sort of the wrong answer, it's probably the way that you're punching it into your calculator. So make sure to use that EE button and stuff like that. So I think this is where we left off. So we'll pick up here. We're going to talk a little bit about strong electrolytes in relationship to acids and bases. And if you remember from Chem 50, hopefully an electrolyte is something that will break apart into solution and basically produce ions. And those ions do have the capacity there to help that solution conduct electricity really well. So something that's a strong electrolyte, when it goes basically for a swim, it will 100% break apart into ions. So something like sodium chloride, that's solid. If you dissolve it in water, you get 100% sodium ions and 100% chloride ions. So what you have in that solution, again, is 100% of these ions. You have none of these whole units still together. And that's why it's a very good electrolyte, a very strong electrolyte, because it 100% breaks apart into ions. And because it produces a lot of ions really quickly, it's able to conduct electricity really well. And is why it's also a good conductor, obviously, of electricity. A weak electrolyte, on the other hand, is something that does not 100% break apart. It actually mainly stays together. And we usually can see that with these reversible arrows. Usually will indicate a weak electrolyte. And unlike a strong electrolyte in solution, this is mainly what you have. But you do have a little bit of these guys. So you got a few of these ions kind of floating around. So because you still are able to create a few ions, it is still able to conduct electricity, but nowhere near sort of what a strong electrolyte could do. So perhaps if you remember talking about this maybe in last semester, usually they show pictures of light bulbs. So like a strong electrolyte will be very, very bright light bulb conducting electricity. Weak electrolyte, the light bulb will still come on, but be very sort of dim. And there's also non-electrolytes, which obviously do not produce any ions, and the light bulb stays on. So acids kind of are the same situation. We have strong acids, which are strong electrolytes. We also have weak acids, which are weak electrolytes. And we have strong bases and weak bases as well, which act the same way. So some strong acids here. HCl, HNO3, which is nitric acid. HCl O4 is perchloric acid. H2SO4, which is sulfuric acid. So in solution, these guys 100% sort of break apart into their ions. And these are ways that you can basically represent that dissociation in a reaction form. So earlier we were talking about the difference between H plus and H3O plus. So here, if we take, for example, our HCl, this is really just showing that the hydrochloric acid is breaking apart or dissociating in water. And when we include the water here, the water is acting as our base, so it's accepting the H plus. And because we chose to include the water in the reaction, that is how we generate the H3O plus. You can just as easily, for any of these reactions that we see here, write the dissociation like so, and it's perfectly fine. HCl goes to H plus and Cl minus. So these are both really the same reaction, just one includes water, one doesn't. A lot of times people will not include the water in the equation for the dissociation of a strong acid, and that's again how you get H plus on the product side versus H3O plus when you have the water. Again, you could do it either way, is perfectly fine. I personally will probably show acids this way, where I just break them apart into H plus and Cl minus. That's essentially what makes something an acid, is H plus and some type of negative ion together, basically. So I usually will show it sort of like that with the H plus, but again, you can include the water, is perfectly fine. So all these guys, pretty much 100% will have these ions here. So we'll have H plus Cl minus, H plus NO3 minus, H plus ClO4 minus, and H plus HSO4 minus in this particular case. So these are some strong acids. Again, hydrochloric acid, nitric acid, perchloric acid, sulfuric acid. A couple of others maybe to add, HBr is a strong acid. HI is a strong acid as well. So these guys are also strong acids. So all these guys, when they go into solution, pretty much will break apart 100% into their ions. None of the whole units will still be there. And again, that's why they are considered a strong electrolyte, but more importantly, they're considered a strong acid because of that, because pretty much all they need to do is go for a swim. Once they go for a swim, they're going to produce a lot of free H plus. And that is really your basic definition of an acid, is the ability basically to produce that. So all they have to do is go into the solution and they produce a lot of it. And since they produce a lot of it, that means that there will be a lot of free H plus. That means also the pH will probably be a little bit lower as well. There are some acids, again, that are weak acids, and we can represent these equations as well in a couple different ways. One way that we see here, again, we included the water in the reaction. That is why we have the H3O plus. So for example, for the first one, you could have just as easily went HF, H plus, and F minus. So again, this is the exact same equation. Basically, they're equivalent to each other, and I probably will most of the time write it like this. Again, you get the H plus versus the H3O plus. This is a weak acid in all these cases. We see these reversible arrows in each of them. And what that means is, unlike our strong acid, what we mainly have in solution are these guys. So these are mainly what's in solution. So HF, which is hydrofluoric acid, nitrous acid. These are the guys that are typically going to be in solution. We will produce a little bit of these guys on the right-hand side. So we'll produce a little. And because it's still able to produce a little bit of H plus, it is still considered an acid. But again, nowhere near something like a strong acid would be able to produce. Because again, a strong acid, 100% going to break apart. These guys, in terms of the equilibrium, sort of leaning more towards this way as it kind of stays together, but will break apart a little bit in terms of ions. Now, in terms of bases, strong bases work pretty much like strong acids. And so we got things like sodium hydroxide, potassium hydroxide, barium hydroxide, and they 100% again going to break apart into our ions, going to produce a lot of OH minus really quickly. Obviously, as the OH minus concentration goes up, the H plus concentration will go down, and the pH will go up in that particular case. And a lot of our strong bases have hydroxide in the actual formula. And if you look on the periodic table, most of those are group 1 or group 2. Group 1 is the alkali metals. Group 2 is the alkaline earth metals. And again, alkaline means basic. So alkaline means basic, and hence alkali metals, alkaline earth metals. So when those guys react with water, they tend to produce a lot of bases. So if you kind of go on the periodic table, like where sodium is, and then potassium, then there's like calcium and strontium and barium. You know, a lot of our strong bases are like right there. Those guys with hydroxide will make a lot of strong bases that we typically see. We also have weak bases, and in terms of actual writing the equation, When we do write reactions for bases, especially weak bases, those are typically the ones I do recommend making sure that you include the water. Um, a lot of times people really struggle with writing the equation for a weak base, and a lot of times the water is very helpful to have in there. And again, the water here is going to act as a acid in this case, going to send the H plus over. When it does, it gives us HF and OH minus. Again, in this case, most of the time going to be hanging out with these guys, but will produce a little bit of hydroxide. And because it's able to produce a little bit of hydroxide, we do get it to be a base. So NH3 is an example of a weak base as well. When NH3 reacts in water, it makes NH4 plus and OH minus. And again here, accepting the H plus from the water in this particular case, going to generate our hydroxide. Again, examples of weak bases. And again, I would recommend in this particular case to actually put the water in the equation, because very often people have no idea how to write the rest of it. So it's a good time to do that. Now, when we think about sort of our acid and conjugate base pairs that we talked about when we talked about Bronsted-Lowry definition, a reminder that the Bronsted-Lowry definition of an acid is a proton donor, so something that will give away an H plus, while a Bronsted-Lowry base is a proton acceptor, somebody that will accept an H plus. There is a relationship between the acid and its conjugate base, or the base and its conjugate acid, and it's really an opposite sort of relationship. So the conjugate base of a strong acid has no measurable strength. So when we think about sort of our acid base, conjugate acid and conjugate base, our relationship between these two, if the acid is a strong acid, its conjugate base will be relatively weak. And if the acid is a weak acid, its conjugate base will be relatively strong. So there's sort of an opposite relationship between those two things. So if you have a weak acid, its conjugate base will be relatively strong. And if you have a strong acid, its partner on their side, conjugate base, will be relatively weak. And the same thing works for bases. If you have a weak base, as it says there, its conjugate acid will be relatively strong. And if you have a strong base, its conjugate acid will be relatively weak. And this is an important sort of relationship to keep in mind, especially later on in this chapter when we talk about salts, this sort of opposite relationship. You want to think about where something comes from, and if it's strong, its partner will be relatively weak, and if it's weak to begin with, its partner will be relatively strong. What that means is, as we will see a little bit later on in this chapter, is there is potential that when something is formed as a result of an acid-base reaction, that some of the products may continue to react and affect the pH of that solution. And that is what is referred to as hydrolysis, because they typically will react with water. And this relationship is an important relationship to understand when we get to that part, that if it comes from something that's strong, it's going to be weak and not really going to react. If it comes from something weak, it will be relatively strong as partner and will continue to react. So H3O plus, and it's the strongest acid we could have in solution. OH minus, strongest base we could have in solution, in terms of their representations. Here's a table from your book, and it lists some strong acids, some strong bases, and again, you can see sort of a opposite relationship in terms of if it comes from a strong, then its partner will be relatively weak. So what I mean by that is here's a strong acid. Its partner on the other side there is a relatively weak base, as opposed to down here we have a weak acid, a relatively strong sort of base. So opposite sort of relationship happening here. Here's a lot of the ones that we talked about in terms of strong acids up to here our nitric acid, our hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and perchloric acid, and some of our weak bases on the other side. So again, this diagram just shows the relationship that occurs when we have a strong acid or strong base. Again, going to 100% break apart into ions. That was what we see on the left-hand side there. When we have our hydrochloric acid in solution, we pretty much have 100% of these guys. None of this is still left. And that is very different than a weak acid where we pretty much have mainly all that there, not so much of those ions that are being produced on the right-hand side. All right, so let's talk about sort of these guys here. So sometimes what that means is some of the examples that we've done up until this point have been more generic sort of examples where they say, hey, the H plus concentration is this, the OH minus concentration is this, what is the pH? So sometimes they may actually just give you a formula for an acid or a base and ask you to calculate the pH. And if it is a strong acid or strong base, you basically can use the formula to figure out the concentration of what you need, and then you could calculate the pH. So why don't you take a few moments and give that a try here. These are both strong acids and strong bases here. So why don't you try to figure out what is the pH of each of these solutions and see what you come up with. So take a couple minutes and give that a go. Okay, let's take a look here and see how we're doing. So in this case, again, a little bit different. They do give us the actual formula here, and we should recognize that as a strong acid. And what that essentially means is HNO3 will 100% dissociate into H plus and NO3 minus, since it is a strong acid. And since we're looking for the pH, which is minus the log of the H plus, what we really need to figure out is what is the H plus concentration here. And we know that the entire thing here is 2 times 10 to the minus 3 molar. When we look at it, it is a 1-to-1 relationship. So as you probably learned in Chem 50, and I think we talked about, if you're trying to figure out the concentration of ions, the way it works is kind of like stoichiometry. So since it's a 1-to-1 relationship, that means the concentration of the H plus would also be 2 times 10 to the minus 3. And the nitrate would also be a 1-to-1 relationship, which means the concentration of the nitrate would also be 2 times 10 to the minus 3. In this particular case, we're just interested really in our H plus. So now that we know what the H plus concentration is, we could go into our pH, which is minus the log of 2 times 10 to the minus 3, and looks like a 2.7 in terms of the pH. 1 sig fig, 1 decimal place here, and 2.7 should be acidic, and that makes sense since we're dealing with nitric acid. So any questions on that particular one there? Okay, so if we look at our second one here, this is barium hydroxide, and this is going to be a strong base. So the barium hydroxide will break apart as well, 100% into barium ions and a couple of hydroxides when that breaks apart. And again, here we're interested in the pH, but we have hydroxide, so we can get to the POH first and then get to the pH by figuring out the hydroxide concentration. And the hydroxide concentration would be found kind of the same way. This is 1.8 times 10 to the minus 2 molar. It's a 1-to-1 relationship here. Not that we really need the barium's concentration, but it would be 1.8 times 10 to the minus 2. But when we look at the hydroxide, it's a 1-to-2 relationship. So what you need to do is actually multiply the concentration by 2 to get the correct hydroxide concentration. And that would be 2 times 1.8 to the minus 2, 0.036 would be our hydroxide concentration. That's going to allow us to get not the pH, but the POH is minus the log of the OH minus. That's going to give us minus the log of 0.036. That will give us a POH of 1.44. Again, for some reason, if you thought this was the pH, it should not make sense to you because 1.44 is definitely not a basic pH. So to figure out the pH, we would then need to use our 14 minus the POH. Going to give us 14 minus 1.44. 12.56 in terms of our pH, and that makes much more sense since this is again a base and that is a basic pH. Question on that one there. So again, you want to make sure that you get the correct concentration here. So when you have the concentration of the whole thing and you're trying to figure out the ions, you could do it just like stoichiometry. So if it breaks apart into a 1-to-1 relationship, the concentration will be the same. Breaks apart into a 1-to-2 relationship, it will be 2 times it, 1-to-3, 3 times it. And just to show you why that really is, if you do, just to really show you how we get there, and sort of the long part of it is when we take 1.8 times 10 to the minus 2 moles per liter of barium hydroxide. We do the stoichiometry part, which is 1 mole of barium hydroxide gives us 2 moles of hydroxide. The moles of barium hydroxide count out. You end up with moles per liter of the hydroxide, and we basically end up with 1.8 times 2. So that's why we basically multiplied it by 2 there, is basically the stoichiometry part of it. Questions on that? So sometimes you may be given the actual formula, and if you could recognize it as a strong acid or strong base, you really just need to figure out either the H plus concentration or the OH minus concentration, and then use either obviously the pH or the POH and the pH formula to figure it out. Any questions? Okay, so let's then talk about what happens though if we're not dealing with a strong acid or strong base. So it's a little bit more complicated, the calculation that involves the pH of weak acids and weak bases. So if we look at, and again, that's from your book, some strong acids and strong bases. And again, you can see the ones that we talked about there on the left and also the ones on the right. That's essentially group 1 and 2 on the periodic table is where you hit all those kind of strong bases. Again, kind of going from group 1 down, hang a right at potassium, and then go down on the other side, group 2, and that'll get you your strong bases. But if you have a weak acid that can be represented by either one of these formulas, so again, we can represent it by including the H plus, or the H2O, which will give us the H3O plus, or just looking at this equation. This is a reversible reaction, and reversible reactions means equilibrium, and equilibrium means what we were talking about in the previous chapter, the equilibrium constant. So we can write an equilibrium constant for this, which is known as the Ka value. Ka, surprisingly, for acid. So we'll add this to our big growing list of K values. We've seen Kc, we've seen Kp, we've seen Kw. Here is Ka, which again, they're all pretty much the same. They're all equilibrium constants. They're all products over reactants. So here, when we take our products over our reactants, we get H plus times A minus divided by HA. If you were to write it for this one with the water included, because water is a pure liquid, it would not be included, and it would be H3O plus times A minus divided by HA if you did it the other way. So our Ka value is the weak acid equilibrium constant, is the acid ionization constant. And as the Ka value increases, the strength of the weak acid also increases. So just be clear on that. When we're talking about Ka values, the higher the Ka value, what that means is larger K value means more products. More products means more H plus there. More H plus means it's a stronger acid, right? Or a better acid, I guess, in that sense. So that's why when the Ka value goes up, the strength of the weak acid goes up. A weak acid is still much weaker than a strong acid. So when we're comparing that value, that is just for comparisons of a weak acid to another weak acid. Again, higher the Ka value, the stronger the weak acid. Would we expect to find a equilibrium constant or Ka value for a strong acid? The answer is no. You would not find a Ka value for a strong acid, because a strong acid will, much like hydrochloric acid, 100% break apart into ions. There is no back and forth. It's basically a one-way street heading to the product side. So because there's no back and forth, there's no equilibrium that gets set up. And because there's no equilibrium that gets set up, no Ka value. So no Ka value for anything like that. Because of that, it does not set up an equilibrium. So when we deal with Ka values, we're definitely dealing with weak acids. And that's one big way sometimes people ask, you know, how do I know it's a strong acid versus, say, a weak acid? That's a big hint. If you see a problem where They give you the Ka value, or if you're able to look it up on a table and see a Ka value, that's a pretty good big hint that it is a weak acid, and you need to solve it as a weak acid. So again, that's a good way to kind of figure out, is it a weak acid or a strong acid, kind of based on that. Now, because it is an equilibrium, and when we do get to equilibrium, we do have to solve these our favorite way, which is basically we're going to have to use ice tables to help us solve the pH of a solution. And we'll talk about that in just a second, but here is a table from your book. And again, these are some weak acids from your books and their Ka values as they go through it. Some acids have more than one proton that comes off at a time. And they do come off one at a time like we talked about before. And there is a Ka value for each of those protons that come off, as you can see in that particular example there. Here's some more from your book and some more from your book as well. So let's take a look at when a problem that involves a weak acid and if we wanted to solve for the pH. So again, we know this is a weak acid because when we see HF there, A, I know that's a weak acid just by knowing it, or B, I could look in a table and find a Ka value like I see there, 7.1 times 10 to the minus 4. Or if I don't want to look in the table and I just see the problem and it gives me that, I know right off the bat that this is definitely a weak acid. So what that means is because it's a weak acid, it is not going to 100% break apart into H plus and F minus. And what that means is because it's going to go back and forth and eventually reach equilibrium, I really don't know what my equilibrium concentration of H plus will be by just looking at the formula. So to do this, we do need to do an ice table to help us out and solve it. The good news is we work these ice tables exactly the same way as we did in the previous chapter. The only main difference here is we're not usually interested in what everybody's concentration is at equilibrium. We're actually just interested in the H plus concentration because that's going to allow us to calculate the pH. So we want to approach this the exact same way as we would approach any other sort of equilibrium type problem. And again, the difference here will come at the end. We're not going to be looking for everybody's concentration, just the H plus, so that we can then put it into the pH. So let's go through this one together so you can see how it all works. So the first thing we want to do is just have our reaction here. So it will be H plus. No, it won't. Let's try that again. Help to start with what we're starting with, which is HF. There we go. So HF, again, going to be a weak acid. So we got arrows going in both directions here. I'm just going to write it as H plus and F minus here. Again, if you want to, you could write it the other way that we've seen, which would be HF plus H2O. The difference here is you would get H3O plus and F minus. Again, it really is your choice. They're both the same. The water is a liquid, not going to affect anything. So, you know, however you want to write it, you can. I personally will do it like I did here originally with the H plus. We're going to do our ice table, and in this case, we're given just 0.5. We'll call it 0.50. 0 and 0. So just like before, if you're not given anything on the product side, safe to assume that it's 0. And also safe to assume in that case, if you're not given anything on the product side, that the reaction is heading in that direction towards the products. And that means that our change would be minus X, plus X, and plus X in this particular case. And that means when we reach equilibrium, we would have 0.5 minus X, X, and X. Any questions on the ice table? So again, very identical to what we did in the previous chapter here. Again, really our main goal here is really to figure out what this guy is at equilibrium. So we really do want to, in this case, figure out what X is. So what we would do here is what we've done before with equilibrium ones. We're going to write our Ka expression, which would be H plus times F minus. divided by HF, and that equals 7.1 times 10 to the minus 4. We're going to put in our equilibrium line into our expression, and if we do that, that will give us x squared divided by 0.5 minus x equals 7.1 times 10 to the minus 4. Just like we talked about in the previous chapter, when I look at my k value here, I see it's relatively small, which means I can make an assumption here and assume that x is equal to 0 because we do have a small value of k working. Again, may work or may not work. And a reminder that when you do that, you cannot get rid of all the x's, just the x's you're subtracting something from. So we will end up with something that looks like this. We're going to multiply the 0.5 to the other side and also take the square root of it. And if we do all that, we will get an answer, hopefully. So if we do all that, let me grab my calculator here. We're going to go 7.1 exponent button, negative button, and 4 times it by 0.5. I'm going to hit equals, and then I'm going to take the square root of it. And if I do that, I end up with 0.019, it looks like, as my x value here. Remember, though, that when we do make the assumption, we do need to check it to make sure it's okay. So to check our assumption, what we want to do is take our x value that we just got. So to check it, we want to take the x value we just got, 0.019. We want to divide it by what we're going to subtract it from, 0.5, and times it by 100%, are the initial concentration, times it by 100%. And if we do that, we end up with something like, call it 3.8%, which means this is a good assumption. Remember, we go by the 5% rule here. So because this assumption is good, and if we go back to our table, we see that x is equal to the H plus concentration, which means that this here is going to be our H plus concentration. And really at this point, that is all we need to figure out our pH. So the pH would equal minus the log 0.019. And that will get us we'll call it 1.7 in terms of our pH in this particular case. Question on that there. We can make sure everything's good. It does make sense. HF is an acid. 1.7 is acidic. So again, if you did something at this point and you got a pH of 10, then definitely something went wrong because that would not make sense. Question on that. So hopefully you could see that it is really the same steps as what we did in the previous chapter. The only different thing here is we're going to use the pH equation basically to figure out the pH, because that's sort of what we're interested in this particular case. Any questions on any of those steps there? Okay. Now, a reminder, as we talked about in the previous chapters, you do want to always make sure that you do check your assumption, because not in all cases will the assumption be good. So again, you may have to, just like in the previous chapter, go back and figure out, another way to solve it, like the quadratic. So for example, if we took like the identical problem and we just changed the concentration to 0.05, what we would have going, and we won't work it out 100% of the way, just to remind you about that. But we would have our initial table here, and we would have 0.05 molar, 0 and 0. Change would be minus x plus x plus x. Equilibrium 0.05 minus x, x and x. This would give us x squared over 0.05 minus x equals our 7.1 times 10 to the minus 4. If we made that same assumption, would give us x squared over 0.05 equals 7.1 times 10 to the minus 4. When we multiply the other side and take the square root, we get an x value of like 0.006 molar, which if we then take and divide by 0.05 times it by 100%, we will get something like 12%, which is a bad assumption. So again, you do want to make sure you check it because it will not always work. It will work a lot of the times, but sometimes it will not. And as we talked about last time, if you don't even want to deal with the assumption and you like something like the quadratic formula, you could definitely just go right into the quadratic formula and solve it. So in this particular case, we would have to go back and solve it using the quadratic formula. So again, just a reminder that make sure that you do check it. And we'll talk why that is in just a bit, why that makes a difference to concentration, but it does make a difference in terms of how much comes off to how big of a part that is of the overall sort of solution in terms of their concentration. So we'll talk a little bit about that in a bit. Any questions on that? So again, just a reminder, make sure you do check them because it won't always work. So as you can see here, when we deal with these sort of weak acid problems, and we'll talk about in a bit as well, weak base problems, they are again essentially work the same way as we would work a normal equilibrium problem, really with the main goal trying to figure out what the H plus concentration is so that we can get the pH of the solution. We will ignore the OH minus concentration because the H plus concentration is well based on the water. And what that means is, and I believe your book that we use now as well does that. Sometimes some books and some people will say when you calculate the H plus concentration or OH minus concentration for your particular solution, they'll say that that concentration of H plus is so low that there's the basic concentration of water that's in that solution is higher. And they look at the contribution of water in terms of the H plus concentration, OH minus concentration. So I would say most people in most cases, including in our class and in our book, we ignore the contribution of water to these problems, and we assume that the major source that can basically affect the pH is what we're dealing with. So for example, if we're dealing with nitrous acid, we assume that all the H plus coming from the nitrous acid is the one that will determine the pH of the solution. The H plus and OH minus coming from water that's in there with it will not be contributing. Some people will say in certain cases it will contribute, and it makes a little bit more of a difficult calculation sometimes because you have to take that into account. So we're not going to worry about that, and I believe your book doesn't worry about it either. So, and again, it's just a situation where you may calculate the H plus concentration. It's like times 10 to the minus 13, and they'll go, hey, water's concentration is way higher than that, so the pH will still be neutral or something like that. So you don't have to worry about sort of water's contribution, so it'll be okay. We do the ice table just like normal. We have that X value that we're trying to find, and in most cases that X value is probably going to be the H plus concentration when you do solve for it. The Ka value is a lot of times a small value, so you can make that assumption, and a lot of times, just like we did in the previous problem, the assumption will be okay. But again, you should check it because the concentration is important in this situation, and it may not be okay, as we saw in the last little thing that we looked at there. So you want to calculate the concentrations of everybody, but mainly the H plus in most cases, and then you can calculate the pH. All right, so why don't you give this one a go, see what you come up with. We're looking for the pH of the solution of a monoprotic acid whose Ka value is 5.7 times 10 to the minus 4. So see what you come up with. And And if you're not sure, monoprotic acid means it has one H plus that comes off. And if you're not sure what to use for the formula of that, you could use HA as a monoprotic acid. So you could use that as the formula. All right, so take a few minutes to see what you come up with. Hopefully we'll come up with the same. take a look and see how you're doing. So again, if you're not given a sort of formula or who it is, monoprotic again means that basically it has one H plus that'll come off. So HA again is that representation of that. And we know it's a weak acid because we do see a Ka value there. So we would have something that looks like this in terms of the formula. If it was a diprotic acid, it would have two H's to come off. It would look something like that. And if it was like a triprotic acid, it would look something like that, where H3A would be there. In this particular case, we'll do our ice table. Since we're only given our HA, that is going to be 0.122. Just like normal, we could assume these guys will be 0 at this point. Change would be minus X, plus X, and plus X. That means when we reach equilibrium, 0.122 minus X, X, and X in this case. Any questions on the ice table setup? Again, very similar to what we did before, pretty much identical to kind of what we did before. Just like before, we also want to write again here our Ka expression, which would be our products, which would be H plus times A minus divided by HA. This would equal our value of 5.7 times 10 to the minus 4. We then can put in there our equilibrium line. That'll give us x squared. 0.122 minus x would equal 5.7 times 10 to the minus 4. We can do and assume x is equal to 0, and that would get us x squared divided by 0.122 equals 5.7 times 10 to the minus 4. And if we do that, when we solve for x, so we're going to take 5.7 to the minus 4 times it by 0.122. Also take the square root of it. It's going to give us something like an x value of 0.00834. We do want to check it. So if we take that and divide it by 0.122 times 100%, again, dividing by our initial concentration, and times it by 100, we do get something like 6.8%, which makes us very sad because this is not a good assumption in this case. So we pretty much cannot do that. So we do need to go back and solve it another way. So we need to go back basically and probably do the quadratic formula in this case. And if we do that, we'll go back to we'll go back to our x squared over 0.122 minus x equals 5.7 times 10 to the minus 4. We're going to multiply everything to the other side. That's going to give us x squared equals we'll call it 6.95 times 10 to the minus 5 minus 5.7 times 10 to the minus 4x. And again, just multiplying everything down here to the other side. Bringing everybody together on one side will get us x squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 equals 0. That would be our quadratic. Going into x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2. Putting in some numbers here gives us minus 5.7 times 10 to the minus 4 plus or minus. I'm going to clean up what's inside the square root part. So I'm going to take 5.7 to the minus 4 and square it. I'm going to minus 4 times 1 times c, which is minus 6.95 to the minus 5. And it looks like if you do everything inside the square root, 0.0002783, you take the square root of that. Looks like perhaps you get 0.0167. That's going to be all divided by 2, I believe, in this case. That's going to give us our 2x values. So doing the plus first, so minus 5.7 to the minus 4 plus 0.0167 divided by 2 gets us something like 0.00807. And doing the minus part, minus 5.7 to the minus 4 minus 0.0167. Oops, hit the right button there. And divided by 2 gets us a negative 0.00864. As we look back at our ice table here, we're interested in our H plus concentration, which is X. So clearly that means we cannot have a negative X. So this right here should be our correct value for X. And that means that this should also equal our H plus concentration if we go back to our table. And if we do, then we can go pH is equal minus the log of the H plus, which would be minus the log of 0.00807. And that will get us 2.09, looks like the pH in this particular case. Any questions on any of that there? I will say in this particular example, I think if you just blew right by the assumption part and didn't check it, you will get a pH very close to this, but technically it would be wrong because it is too big to do the assumption. And that happens sometimes. It just depends on the problem. It won't always be that way, but it just happens to be very close. If you did the assumption or not the assumption here, because it was only 6% difference. So it's right there on that kind of grayish area. But you definitely should solve it using the quadratic formula here based on the 5% rule. Also makes sense since this is an acid, pH of 2.09 is acidic. So that all works out okay. Question on any of those steps, where any numbers came from, why we did any of the numbers? Any questions on that? Okay, so since you're professionals here, why don't you do this one here? Calculate the H plus concentration in 0.01 molar. And while you're at it, why don't you also do, why don't you figure out the pH as well? Perhaps the right answer is up there, maybe. We'll see. Okay, so let's take a look at this one. So again, we know it's a weak acid. We have a Ka value given to us, so we need to do an ice table here. We have HCN. So we have our HCN. Again, going to break apart into H plus and Cn minus. And we are starting with 0.01 molar. So initially here, 0.01, 0 and 0. Change going to be minus x plus x plus x, which means at equilibrium 0.01 minus x, x and x. At this point, we'll go into our Ka expression, which is our products, which is H plus and Cn minus, divided by HCN, and that is going to equal the equilibrium constant value they gave us, which was 6.2 times 10 to the minus 10, looks like. We're going to take our equilibrium line here and put it in. So that gives us x squared over 0.01 minus x equals 6.2 times 10 to the minus 10. It's a small k value here, so I'm going to give it the old college try here and assume that x is equal to 0. That's going to give me x squared divided by 0.01 equals 6.2 times 10 to the minus 10. I'm going to multiply the bottom to the other side and also take the square root of it. And if I do that, I end up with 6.2 exponent negative button minus 10 there times 0.01. And that is going to give me 6.2 times 10 to the minus 12. I'm then going to take the square root of it. And that will give me an answer of, looks like, excuse me, 2.5 times 10 to the minus 6. Again, we do want to check it. So we're going to take this and divide it by what we were going to subtract it from, or the initial concentration, times it by 100. And if we do that, we're like something like 0.02%. So this was a good assumption. That means when we come back to our table here, we see that the H plus concentration will equal 2.5 times 10 to the minus 6 molar. That was answer number 2, I think, on the list there. And since I asked for the pH as well, the pH then would be minus the log of 2.5 times 10 to the minus 6. And if we do that, looks like a 5.60 as our pH. Also, 5.60 is acidic, so that's all good, and it makes sense there as well. Question on that particular one there. Question on Ka type problems. So hopefully you can see that Ka problems are really, again, still the same type of problem, still equilibrium problems. The only real difference is here we kind of use the pH equation at the end and get the pH of the solution rather than just everybody's concentrations. Any questions on any of those there? Again, you would supply the same sort of approach like we've been doing, either make an assumption, maybe you get a perfect square, use a quadratic formula to sort of solve these guys. Okay, so no questions, then we will talk about percent ionization. So percent ionization is calculated as above here. The percent ionization is the concentration of H plus divided by the initial concentration of the acid times 100%. Essentially, when you calculate the percent ionization, that is essentially how we check our assumption. So this is really how we've been checking our assumption is we take our X value, which in the case of an acid is the H plus concentration, and we divide it by the initial concentration times 100%. Percent ionization is basically how much of the acid has broken apart. So when you have something as HA, it is basically how much of this guy has come off. So sometimes it's referred to as percent ionization. Sometimes people call it dissociation, how much the acid dissociates. Those are all just fancy words for how much basically H plus comes off in this solution. The difference between a strong acid and a weak acid, as we've been talking about, in a strong acid, as you can see on this graph, 100% of it dissociates and come apart, as opposed to a weak acid where not 100% of it comes apart. But if you remember a couple of things that we saw earlier today, the concentration of the acid plays a big part in terms of the percentage of ionization that occurs. And what we see is the bigger the concentration of a weak acid, the less the percent ionization is, versus the smaller the concentration, the higher the percent ionization. So you may be asking, why does that make a difference? So we saw the actual difference of that with that first example we did today. I think it was HF. And if you remember that when we had the concentration of 0.5 molar to begin with, our assumption was all good, right? We assumed X is equal to 0. It was like 3%-ish, 3.7%, something like that. So it was good. And that was different than when we took the exact same acid, kind of the exact same conditions, and made the concentration 0.05, right? Almost like, a lot less. And when we did our assumption and we assumed that X is equal to 0, we got something like 12%, which was bad. Yeah, this part was good. And that's what we see here in this graph. At a higher concentration, less of it is coming off versus a lower concentration, even though less of it's coming off, it's a bigger percentage. So it's kind of like the pizza example, right? If you got a brand new pizza, everything's good. Somebody takes out one slice, it's not that big of a deal, right? You still got almost the entire pizza still there. It's not a very big percentage. But then you get the horrible thing that always occurs with a pizza, right? You got like one slice left, right? Or two slices left, maybe. And obviously, if you take one slice out of that pizza, that is a much bigger percentage of what you started with than it is when you take, say, the one slice here. And that's why when we do these sort of checks in certain cases, you may say, hey, it's like the same acid, concentrations, it's different. And in one case, like in the 0.051, even though they're both going to give off HF, a little bit of ions, that little bit that's given off when the initial concentration is 0.05 is a bigger percentage of where you started than if you started with 0.5 and that little bit comes off. It's a much smaller percentage of the overall and based on where you started with. So concentration is really important. It affects obviously how much comes off. So if you start with just a little and lose a little, that's a big amount, right? In comparison to where you started. Then if you had a whole bunch of something and you lost a little, it's not as big of a percentage. So percent ionization helps us sort of understand why in certain cases as well. In addition to just telling us how much of the acid has broke apart, it also helps us understand, why in certain cases maybe sometimes an assumption will work and why in certain cases sometimes it will not. Question on that. So let's take a look at a problem that involves percent ionization and sort of a way we can kind of work it out here. If we wanted to know, we have a solution of formic acid is 0.47% ionized. In this case, we're actually looking for the Ka value. So we want to actually find what is the Ka value. So to sort of show you what's going on here, we're going to approach this the same way as a normal weak acid problem. Obviously, this is a weak acid because we're looking for a Ka. Otherwise, it would not be a weak acid. So we're going to start it the same way. So we're going to do our HCOOH. It's going to break apart into H